Everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. So today we are going to look into the physical layer of white column stores, HBase. The bell is ringing now. Just as a reminder for the logical model, so for those of you who were not here yesterday, so the recordings will be released just a bit later today, but this is the logical model quickly. The idea is that it's the relational model. It's very close to the relational model. It looks like a table, but there are a few differences with relational database systems because it's slightly on a lower level, which enables us to do that on 10,000 machines. The idea is that first you notice that the columns are actually split in column families. It's not just columns like there is in a relational database. There's multiple column families. And you will understand why when we look at the physical layer, it's actually interesting to have column families because it's going to make it faster if you only look at specific column families, right? So the column families corresponds to the colors, purple, yellow, and red, and then you have column names, but the columns, you can just create them on the fly. There is no schema or anything, right? So the only thing you know at the meta level is the name of the column families, but the columns is really something that you create on the fly as you insert the data. The other thing is that there is exactly one primary key that consists of exactly one column, that's the row ID, right? So these are sorted. And the row ID uniquely identifies the rows. So to identify a cell, you need a row ID, you need the column family, and then you need the column qualifier, right? And then possibly a version, if you want to consider use the versioning system that it has, right? Multiple versions of the cells. That's it. And so what you store in the cells can be as large as 10 megabytes without any problem. And we saw it can be XML, JSON, pictures, anything you want, but it's also fine to put small values in there, just like a relational database. There are no types in there. There are no column types like integers, varchar, dates, and so on, like you would have in PostgreSQL. Everything is just sequences of bytes, right? But of course, when you use it through APIs via programming languages, they will add some convenience layers in order to support types. But as far as HBase is concerned, the row IDs are all sequences of bytes. These are sequences of bytes. The column family names are sequences of bytes. Everything is a sequence of bytes, right? Okay. And then we saw, in order to partition things, because you know in big data we love to partition things because this is how we spread it all over our cluster. We saw that in the case of HDFS, we partition the file contents in blocks. And here we are going to partition it just as I explained yesterday as a wedding cake, meaning that we partition it horizontally in intervals of row IDs because I told you this is sorted, right? So you have a min and a max. By convention, we take the min inclusive and the max exclusive, right? Because the max exclusive is the min inclusive of the next interval. And that's called the region, right? This horizontal partitioning is called the region. And then we also cut the wedding cake vertically by column family. And when you have the intersection of one region, one interval of row IDs here, intersected with a column family, you get here what's called the store. And this is the level at which we are going to be storing all of these cells, as I will explain in details today. Now, what about the architecture and the machines that we connect? Who knows Dinner for One? We watch it every year on December 31st. If you haven't, then you can watch it. But anyway, the same procedure as every week, I could say. So we use this centralized architecture. For HDFS, we had the name nodes, the name node and the data nodes, right? These are processes that run on machines. But since these are processes, we can run other processes. And in that case, there is a process called the HMaster that typically runs on the same machine as the name node. Typically, doesn't have to, but I mean, people do that. And then you have the region server processes that run on the same machines as the data nodes, right? These are just processes on the same machine. And that makes our life easy because it's the same machines that store the data via HDFS as the machines that take care of the HBase service, if you consider that HBase is a service, right? And it's very good because it means that, remember, the blocks are stored on these machines. And since it's the same machines that will serve the HBase request, that's quite convenient because we will see that we can very often just read the data locally. It's called short-circuiting. But technically, do not forget that even though they are physically on the same machines and we can short-circuit a few things, HBase on the logical level is still above HDFS, right? HBase is a client of HDFS. All of these processes here are clients of HDFS. All right, so this should be easy. The only thing you need to do is learn the new names of these processes, and I'll have some in a couple of weeks. I'll have new names again for other technologies. All right, so what's important is that the region servers are just services. They serve regions. They are responsible for regions. They don't store any data because where is the data stored? In HDFS. Right? So it's all going through HDFS for the actual storage. Okay, so let's start with the HMaster, which is the coordinator node. What is it responsible for? Well, it shouldn't surprise you because it's very similar to the name node in HDFS. All the high-level metadata operations, that's the HMaster. So for example, if you want to create a new table, if you want to drop a table, if you want to create column families, remove column families, and so on, that is all done by the HMaster, and this is known also as DDL operations, right? Data definition language. It also exists in relational databases. It's when you create your tables, drop your tables, add columns, remove columns, and so on. All right? Okay. And I will take this opportunity to answer one of the questions, maybe I can do the other two as well, about, I said you can add and remove column families with through the coordinator node. What about single columns? One of you asked yesterday, can I do that? The answer after, so Martin investigating, so thanks very much for looking into this. The idea is that there is indeed a method called delete column in the API, in the Java API of HBase. However, it's very inefficient. And you will understand why when we have looked at the physical storage. So you can say, I want to delete column 1 in the column family yellow, right? But it's going to be very inefficient because this data in the columns is basically spread all over the cluster. So the only way you can delete that column is go through the entire data over the entire cluster and remove it wherever you find it. Very inefficient. So I think they added the method as a convenience for anybody who wants to do it, but don't expect this to be done in 1 second. That's not how it works. However, deleting and adding column families, that's a bit quicker. Why? Because they are grouped together, as we will see, right? So this is the reason why at the level of column families, it's much faster. Okay, and that is the difference with a relational database system, because in a relational database system, you can add and remove columns via the schema on the meta level. I'm not saying it's going to be fast because you still have to go through the tuples to really remove it or add it. Yeah, so it's really the column families that are here handled at that level efficiently. All right, next. Imagine that you have this table and we have billions of row IDs in there, and maybe doesn't matter, but let's say millions of columns, just very sparse, a lot of empty cells in there. Now, I told you that this space of row IDs is partitioned horizontally into regions, which are intervals of row IDs like this. So you can see there is, this is one region, 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 right? So this is all partitioned horizontally like that. And the idea is that every one of these regions is going to be assigned to a region server. What that means is the region server is responsible for handling all of the requests that have anything to do with that region, right? For example, the white region is handled by the third region server, which also handles the blue region. The purple region is handled by the second one, so does the red one, the very poor choice of colors, I'm just going to show. But anyway, you see the arrows, right? So this is handled here, also here. This one is handled by this region server. These two are handled by this one, and so on. But it doesn't need to be contiguous, right? For example, here, these two regions, it's this one and that one. They don't need to follow each other. All right? Is that clear? We just assign, right? So it means that whoever needs values from these regions will have to go to the region servers that handle it.
We have a question. Are these regions assigned automatically or are these regions assigned manually?
This is done by HBase. As a user, you don't need to worry about that. It's all handled by the region server that just distributes the responsibility. Yes?
Do we also create like replicas for the partition of the table?
We don't. Do you know why? Can you guess why? Remember that there's HDFS below where the data is stored. Anybody? Yes? So you're saying it's already replicated basically in HDFS, right? Yeah, this is the idea. So since HDFS is already taking care of replicating, we do not need an additional level of replication on top of HBase. So this is the reason. It doesn't mean that we don't back up anything or that we don't take a few precautions, but replicating the regions is not one of them, right? Does it make sense? Okay. And by the way, that's also the reason I think every year somebody asks, I think one of you also asked this year, but if you consider using RAID, right, redundant array of inexpensive disks, right, it's totally useless with HDFS precisely because we have this replication. Yes?
So if one region server is in charge of one row, then it will act as a client for HDFS and it will...
Exactly. Yeah, exactly. The idea is that we have multiple layers, right? So now we have 4 layers, in fact, now. The layer above is you using HBase, right? Then there is the HBase layer of which you are the client, right? And then HBase serves the clients. Then there is the HDFS layer. Relative to this layer, HBase is the client and HDFS is the server. HDFS itself is stored on physical drives on the processes. So you see, there's you, there's HBase, there's HDFS, and there's the physical machines. That's already 4 layers. Whenever you think at this, you look at these things, you really need to always put yourself on some layer, and relative to one of these layer separations, there's always going to be a logical layer and a physical layer. But depending on where you are, a logical layer from the perspective of below will be the physical layer from the perspective of above, right? And in fact, because we do things this way in computer science, we can build huge things. That's exactly because we build in these layers on top of each other that we're able to do that. And there are even layers coming on top of HBase that add back SQL and the relational algebra and so on, right? That these are even upper layers. But we nicely separate things. It's just like when you build a house, right? There's the people who do the masonry, there's the people who come from the electricity and so on, the plumbers. So this is all separated, and we all focus separately on the pieces of the puzzle, and then we put the pieces together, right? Yes? Not necessarily, but still often. It's a good thing when they are collocated because it's going to be much faster, more efficient, but it doesn't always happen, and sometimes you're just a bit slower. But I will say also a few words about that because this is actually a very important feature of trying to, most of the time or often, be on the same machine, right?
Like limited size, like 260 bytes.
We will look at, you will understand when we look at the actual physical layer. The idea is that there are the blocks of 128 megabytes at the level of HBase. The files that we will create, because we're going to create files on HDFS, right? These files are going to consist of multiple HDFS blocks, right? But this is a physical detail that HBase doesn't care about, right? It just stores the files. And we'll see that there will also be some sort of logical organization of these files, but this will be specific to HBase, right? I think everything will become clear as soon as we dive into the details, right? Okay. Now, what happens, and maybe that also answers a part of your question, it might be that a region is growing and becomes too big. It becomes so big that things start being slower, right? So what do we do when this happens? We can split it. And this is done directly by the region server. The region server is going to notice that one of its regions is starting to be too big. It's just going to split it into two different regions. It remains responsible for these two regions, but they were split, right? And what happens is that when then there is an imbalance across the servers, then the region server can reassign a region to somebody else, right? Like moving the yellow region there. But this is two different things, right? Splitting a region by the region servers, reassigning a region to another region server. And now also to answer the questions you asked earlier, it might be that here that was collocated, that the data, the actual blocks on HDFS were on the same machine as the yellow region. If we move this over here, that's no longer going to be the case. The data will still be physically on the third machine, but then it's served by the fourth machine, right? So for a while, it's going to be inefficient, but the new data that gets written will be on the fourth machine. So it's going to slowly become faster again, right? But we'll go into these details. I really take the time to drive you through all of this and everything will make sense. What if we lose one of the region servers? That can happen. Then we just reassign the regions. Why don't we care about the data? Because it's replicated in HDFS, right? So even if some of the replicas were all on the second machine, they are still somewhere else, right? The worst case, we read them over the network. There is a question on Zoom.
Do HBase and HDFS cooperate to ensure data locality?
Cooperating?
Data locality.
Yes, they do. In the same, it's Hadoop, right? It's both are Hadoop, so they are designed to work well together, and it means that that the design of HBase is done in such a way that very often you'll have locality, right? And I'll come back to that as soon as we're done with the physical design. I'll explain, and you will see it all makes sense. All right. Okay, so that's the region server, what it does, and how this is assigned, right? So we can just move over the regions. Now let's go to the region servers. So if we look at now our big table, we see that it's partitioned like this, horizontally and vertically, so that I have what I call a store, a store, a store, a store, a store, a store. Of course, it's more than 6, right? It's just for my slides, but in practice, you're going to have a lot of different ones, a lot, especially horizontally. You're going to be, you can really have thousands of regions very easily. The number of column families, it's not going to be thousands, right? Typically, I mean, you have maybe 2, 3, 4, 5, 6 column families, maybe 10, but it's not like you're going to have millions of column families, right? It's the number of columns that we scale, but the number of column families is typically, you can count it on your finger. All right, so let's focus then on a single store, single column family, and a single region. It means we are on a region server, on a specific machine, handling all of this. What is there inside a store? Well, if you look closer, there are cells, right? It's made of cells. We have horizontally, we have the row IDs, right? And vertically, we have the entire column family, but it's made of columns, right? But it's just all in the same column family now, so it's a bit simpler. All right, so now we have 6 cells that are in there. It might be also, there might be versions of them that we might have. So we may have more than 6 values if you also remember some values from the past. And the idea is that all of that, that's the logical layer here, it's all going to be stored on HDFS, right? Persisted on HDFS. What does that mean? It's going to be files, because the only thing you can put on HDFS is files, right? And we are going to call these files H files, right? It's the name that I'll give to them, and we will see what's inside. I will drive you through that, but these are H files. So all of that data that is in this store is persisted on HDFS. The word persisted basically is the idea of storing something on a drive in such a way that even if you cut the electricity and switch it back on, you still have the data. That's the notion of persisting the data, right? So it's persisted on HDFS as H files. Okay. Now, if I look even more in the details of what there is in these H files, this is how it's actually mapped. So I have my logical layer on top. I have my physical layer below. And the idea is that I'm going to have some sort of natural order in the cells that I have here, in the sense that I'm going row by row and then column by column, right? So this one, then 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 this one, right? I'm forgetting about the versions right now. So you see the red one, then the blue one, then the third one will be the purple, the fourth one, the yellow, then the black one comes here and the green one comes there. In other words, we are just sorting lexicographically, first by row ID and second by column name. Who sees that? Right? And we are just storing this in that order in my H file. What are these? You might have recognized key values, right? There is a key and there is a value. What is the key? It's like playing, what is this called where you play and you have the ships, battleship, right? Yeah, that's pretty much like this, right? So you have these coordinates in there. And then A1, let's say, so you put A1 in there, that's the key, and whatever value is in there, you put on the right. In other words, this is yet another key value model, and the H files, in fact, are just made of key values, right? So the key will be the coordinates of where you are in terms of rows and columns, and the value will be whatever value you put in there, which can be an integer, a date, an XML file, a JSON file, a picture, and so on. That goes on the right. Yes? Yes, except that it's sparse and you only store the values that are actually there, right? So if there is one of these cells that doesn't have any value, then you don't store anything, right? And in general, that's the case. You will have billions of rows and millions of columns, but of course, it doesn't mean you have a quadrillion values, right? You will have less than that because there's a lot of sparsity. But you only store physically the cells that actually do have a value, and that's really a small subset of the logical set of cells, right? Over there?
Shall we also store the logical table?
So what we store is a physical representation of the logical table, right? The logical table we don't store anywhere in that way. It's only a visual representation that I drew on my slide. What is stored is really just what you see below here, right? But then what happens is that HBase or the user reconstructs that table from the representation there, right? It's really a reconstruction, logical level, right? In the same way that in HDFS you have the physical blocks, but you still have on the logical level the file that is a sequence of a trillion bits, right? But seeing a file as a sequence of a trillion bits in HDFS is a logical thing. You never ever store these trillion bits as is, right? You only store them in blocks. Here it's the same idea. You store them physically as these key values in the H files, but on the logical level, your view on that is as represented there. Does it make sense? Yeah. Yes?
Particularly because we're talking about sparse data and HDFS, is it still a good idea to use 64 megabytes blocks or 128, or would you go even lower?
That's a good question, and it's true that HBase has a different block size. However, this is totally orthogonal to the HDFS block size. It means that physically on HDFS, you still have blocks of 128 megabytes. That doesn't change. But inside the files on the logical level of HBase, we will have blocks, in fact, that have a size of 64 kilobytes, as we will see, right? So there is this, but you really need to be very careful to not confuse the HBase blocks that I will call H block to distinguish them from the HDFS blocks. And that might raise questions, and that's exactly why I'm going to explain and explain how this all happens. How can it be that we can update the data just like this on the fly and read it so quickly, in spite of it being stored in a system that has 128 megabyte blocks and where you cannot random access in any way, right? This is a big challenge, and they solved that challenge. So this is what I'm going to explain, right?
On Zoom,
yes,
we hear the question: why one H file / store or more? I don't necessarily know what the actual question is.
There can be multiple H files per store, but also that I will explain, right? These are all things that I'm going to go through and explain, right? By the way, there's two other questions you asked yesterday, so just to make sure I don't forget. The size of the row ID So the best practice, so Martin investigating, and the best practice is that the row ID should not be more than 32 kilobytes, right? 32 kilobytes. And in fact, it makes sense because imagine that you have a row ID of 10 megabytes. Imagine the time that it would take just to compare the row ID to see if you have the right one, right? That's really would be extremely slow. So no more than 32 kilobytes for a row ID, and in practice, probably even less. What was the third question? There were three of them. Oh, yes. So the ETH research collection allows you to store zip files on the long term, and it's open source zip. So it's documented. So we assume that the people 1 century from now or a millennium from now, the archaeologists that look into what we are doing today, they will find the open source documentation of zip. Right. That's the assumption. All right. So I answered all three questions. Thank you very much, Martin, for helping out with this. All right. Okay, let me continue to explain this. So now there was no versions in there. What if there's multiple versions? You just store them together, right? So it's sorted by row ID and by column name. But within the same row ID and column name, you might have multiple versions. And here it's decreasing. I have first the freshest version, the one that is the newest of all, version 4, then 3 to 1, and they're all together, right? So you sort by row ID, by column name, and then by version, decreasing. Okay, another thing is that I told about versions, and it means that there is a linear timeline, yes?
You also say like an history of the cell with all the values in it too.
Yes, that's what it means, yeah. We keep the versions and that it has a memory of the past, right? And because of that, because we have a memory of the past, it means that we have a linear view over the data. And that means that it shouldn't be confused with Dynamo, where we had these vector clocks where we could become inconsistent or not atomically consistent. HBase is different. It really enforces this linear timeline. So it's consistent. And it does that by locking things at the level of a row, right? Just like in HDFS, you lock at the level of a file when you write. Anybody who is working on a row locks everybody else out, right? So you can read maybe past versions, but you cannot two people at the same time write data to the same row. This is how we ensure that there is a linear timeline. Okay? All right. So now, going even more physically, is there another question? Yes? No, you can continue to read because the past data is already stored, right? So it's accessible, but you might not see yet what the new data that's being written that you don't see yet, right? But you could totally see the past data. It's no, because only one will be allowed. The other one is locked out. You take a lock, the first one can modify the row, and the other one has to wait for that. Yeah, so it's one at a time for writing, okay? All right, so now I told you this is physical, right? What is at the bottom, but of course, physical, what is it for computer scientists? It's zeros and ones, so we still need to get this into zeros and ones. How do we do this? We just concatenate the key values one after the others, right? So every key value will be a sequence of zeros and ones, and we just put them one after the other. That gives us the H file, all right? What is there in a key value? Now I'm zooming into the actual formats of the key values. Well, I have here a key length and a value length, and then the key, and then the value. Then you could ask yourself, why not just the key and the value, right? Why do we also set the key length and value length? Because we can just see here the key, so we have its length, and we see the value, so we have its length. But it has to do with the fact that the length can vary. And since we just concatenate the key values on disks, it's just a sequence of zeros and ones. So if you just see zeros, and if I directly give you the zeros and ones that are on the disk, how can you reconstruct the key values? Well, you can't, because you don't know where they stop. You don't know the limits between the keys and the values and the next key and so on. So we need something called a prefix encoding for that. So the idea, and here I'm giving you an example, for those of you who were in information retrieval, you've seen that. It's an example of prefix encoding, just to give you an idea. That's called the gamma code. It's an efficient encoding of integer. And the idea is that I can efficiently, just looking at the number of ones here, I know exactly the number of digits to read after that, and I can reconstruct, right? So this is just for those who know the gamma codes, that it works in that way. Who knows the gamma code or remembers the gamma code? Right, some of you. And the others, you don't need to worry, because this is not, we don't use the gamma code in HBase. It's just to connect it there. But another, if I give you another example of prefix code, it's the phone numbers. The phone numbers are a prefix code, because if you dial on your phone, you know exactly when it's going to end, in spite of the length of the phone numbers not being the same, right? If you dial an internal number at ETH, it's 5 digits, right? So you just dial the 5 digits. How do you dial a phone number outside? You press 0 and then the 10 digits, right? So it's 11 digits. But it's done in such a way that even if you're on a landline phone, you just dial and nothing happens. And then suddenly you have the last digit and it starts dialing, right? This is magic. And this is because the design is in such a way that you unambiguously know where it stops. And here it's the same idea, that if you store here on exactly 32 bits, you know it's 32. You store the key length as an integer. Then exactly on 32 bits, you store the value length. Now you can read that. So you read, okay, that's my key length. I know now the length of the key. Then I read the value length on 32 bits. I know the value length. And then I read as many bits as my key length. And then I read as many bits as my value length. Now I know exactly where to stop. Right? So this is the idea. Okay. Now, if I go within the key, now I zoom in inside the key. What do we have? Well, not surprisingly, in a key, you have the row ID, you have the column family, you have the column qualifier, the name, you have the version called the timestamp, and you have a last bit that's actually just to mark for deletion, that I'll come back to. But here we need to do the same thing with the lengths, because the row ID might vary in length, so you don't know in advance how long it is. The same goes for the column family and so on. You don't know the length. So now you store here the length on 32 bits. You know the length of the key, so you read that many bits here. Then you read on 32 bits the column family length, and you know exactly the length here. This is a fixed size. I think something like 32 bits, maybe 64, I think 32. And then it's 1 bit or 1 byte. So there's a fixed size here, a fixed size here. Why don't we have a length for the column qualifier? Yes? It's a subtraction, right? We have here already the key length from here. So we can just do the key length minus this, minus this, minus this, minus this, minus this, minus this, gives you the size right there. Was it your answer? Not exactly. Oh, sorry, I misunderstood you. Well, this is the answer, right? You basically subtract, since you know the overall length, so the key length is all of that, that's the key length. And then you know everything else. By subtraction, you just get the length of the last one. So we are saving a bit of space here. Okay, so that's what we have in a key. And you see that it's lexicographically ordered, the row and the column family, which is all the same in the same server, in the same store. Then the qualifier, timestamp, and the marker for deletion. All right. Now, are we just going to pour this sequence of key values like this in the H file? Not exactly. We just need to add a little bit of index structure to make it easy to retrieve the values in there. And the idea is that when we store the key values, we are going to group them in 64 kilobyte chunks, right? And we call that H blocks, because I don't want you to confuse that with the HDFS blocks, because we still have the HDFS blocks with 128 megabytes. Note that this is a logical block in the sense that it's not cutting bits, it's cutting key values. It's never going to cut a key value in the middle, right? So the last key value, if there's a key value that extends beyond 64 kilobytes, then the H blocks just is bigger than 64 kilobytes. You let the H block go all the way to the end of the last key value, it might be bigger than that. You might even have an H blocks with 10 megabytes if you store an XML file in there, right? But basically, this is what we do. And the idea is that then we build an index on that with a lookup table that directly tells us where each one of these H blocks starts. And then we can efficiently retrieve. If I'm looking for a key, I can load that in memory, that part of the H file that has the high level index. And then I look for some key 14, for example. It's between 11 and 17, so I know that it's right there, right? So this is the idea of why I have these H blocks. It facilitates the lookup. Otherwise, I would have to either do a full scan or some binary search, but since it's on disk, it's not efficient, right? You would have to random access the disk and meet the latency. For whom is that clear, right? So this facilitates looking up the key values because we just load from memory this, and then we know exactly in which one of the HDFS blocks it is. We only read that block. And maybe if we're on the same machine, we can even just read the physical block, the 4 kilobyte block on disk of where that is. All right. So what levels of storage do we have? Now, if I recap what we have. So we have the table, right? But this is over the entire cluster. Next, I partition my table horizontally in regions, right? Can have a few thousand regions, maybe. Then I partition vertically by column family, and these I count on my fingers, but that gives us a store for every region and column family, right? So far, so good. Then my store is persisted in multiple H files, multiple, so that's the answer the question we had on Zoom, right? Multiple H files per store possible, more than one possible. Within the H files, I have my H blocks that contain a number of key values. And again, they are elastic H blocks because they don't stop exactly at 64 kilobytes as you would in HDFS. And within the H blocks, we have the key values. That is my overview of how, so you need to take a mental snapshot of that. This is how it fits. We have key values in an H block. The H blocks are organized in an H file. Multiple H files persist the data for a store. Multiple stores for the column families give you a region, and then multiple regions give you a table. For whom is that clear? This overview here? It's very important. Okay. Now, I'm going to come to the problem and the actual super interesting challenge that there is here. All of that is stored in HDFS, right? It's in an HDFS block somewhere, or multiple HDFS blocks. What if I want to insert a new key value in the middle of that? Right? Somebody comes and says, for example, add a column to, so insert a key between, let's say, key 9 and key 10, right? Right here. I insert a new key because I create a new column, for example, and insert that here. How do I propagate that to HDFS? Well, the answer is you can't do it, at least not efficiently, because you know that in HDFS, there is no way you can just write to the file like that. That would be random access, right? So what you would be forced to do is rewrite the entire HDFS file from the very beginning and overwrite it with the new version of the file just because you wanted to change a few bits, right? So that's not efficient at all. There is something here that needs to be carefully designed in such a way that we are able in HBase to do updates like this in a way that works with HDFS, right? Because again, in HDFS, we can just write the files from the beginning to the end, and that's it, right? Then you can append more at the end, but you cannot just insert in the middle. So these key values there, they're all sorted, right? Lexicographically. So how do we insert new values? In order to do that, you need to understand something. So I have, again, my overview right here with what I have on disk. The idea is that I have these key values in these H blocks, in these H files, all persisted. But I also have the new key values that I've just created. I don't put them in HDFS just yet. I don't persist them just yet. I will just keep them in the memory of the region server. So the quick answer is, if somebody adds new cells, add new values, or modifies something, all of that is just done in the memory of the region server, and we just don't put it just yet on HDFS. So it means that if I have to answer query, I need to look here in the memory, and I need to look here in the H files on HDFS. I need to look everywhere. So what happens? People are going to use HBase, so I assume I have some of the values stored on HDFS, but then somebody updates HBase. They added a value, so that creates a new key value in the mem store. somebody else does. Other people do, oh, the memory is full. What do? We are going to do what's called a flush. We flush all of the key values to a new H file, just like that. What happens in this flush? We need to basically write all of these key values sorted by key, right? And I create also the index and everything. So we sort and we write. In fact, we do not wait for that moment to sort the key values. In fact, already before that, as this happens, we maintained a sorting order in memory. And you know how to do that. We have plenty of structures for that. You can use trees, for example, in order to maintain the order. So technically, you can insert in logarithmic time, for example, and then at the end, you just linearly traverse the tree structure that you have in memory, and in linear time, you can put everything in HBase, right? Who understands that? That's called flushing. I'm flushing the memory, I'm flushing all of the key values in ascending order to HBase. Now, there can be a problem, because what if there is a crash in the data center right before I flush? Everything was in the memory, and then I didn't even get a chance to flush it. So we have to take a few precautions in order to care for that. And the way we do that is that in every region server, we keep a log of all of the requests. So before I put it in memory, I'm just going to log in a journal the new keys that I create, and that's called an H log, right? Everything starts with an H here. So I create an H log, and once I have written to the H log, I put it in the mem store. And the H log I can put on HDFS without any problem, replicate it and so on. The difference between the H log and the H file is, in the H file, it's sorted by key, right? Lexicographically, row ID, colon family, colon qualifier, and so on. In the H log, it's sorted by the order of arrival, right? It's just in the order in which the updates are done. It's just like the edit log in HDFS. Remember the edit log? It's just a journal that second by second keeps track of everything that happens. This will not be sorted by key, which is why it's efficient, because we just append there. And we know that you can append in HDFS without any problem. So this is why we can have this H log in HDFS. Okay, and then we put it on the mem store, then we flush and so on. So if we have a crash, it's no big deal, because it's all in the H log and we can still reconstruct the whole thing. So when do we flush? As soon as some limits are reached. One of them is that a mem store has grown in size so big that what I call a mem store is the memory of a store, right? It has reached a limit, or maybe the overall mem store size over the cluster has reached a limit, and then it feels like this is too much work to fix if there's an electricity shortage. So we flush, or maybe the write-ahead log is full, right? So then you flush too, right? And then if you want to read data to serve the queries, you just need to read from absolutely everywhere. You look in the H files, you look in the mem store, everywhere, then you gather the blocks that you want to return to the client. Who followed? For whom did that make sense today? Okay. I'll still continue next week, because I have a few more things to explain to you, but hopefully now you understand why we are able to do these updates while still writing to HDFS in batches, because this is what it's called, why we flush every time it's a batch. This is batch processing. All right, so thank you very much. Do we still have, yeah, I still have time to just check here, if it will let me. Right here, just check that you followed. It seems that here the network is all working in this room, so it's really E7. Yeah, exactly. Yeah, no lagging, right? Yeah, exactly. So it's really in E7 that we have a problem. Okay, so in this lecture, just so you know, I do expect a few more in the 50 to 79%. This lecture is actually the toughest of the entire semester. So first, congratulations that you've made it so far. This is really one of the toughest, so totally expected. I'll continue next week. We can answer all of your questions, ask them on the Moodle, write to us. We will be happy to help you, right? All right, so thank you very much. I'll see you next week on Tuesday.